So I want to start by telling you about the UI Computing Conference, which I've mentioned before. This is a project that the student ACM chapter runs every year. And this year's conference is going to be on February 25th and 26th. Now, usually, we would have a Friday evening keynote and then a social event. And then on Saturday, there would be 3 talks or 4 talks and another social event. And this was all done in person, and it was kind of a 2-day affair, and people came, and we had door prizes and games, and it was kind of a big deal. Unfortunately, for the last 2 years, we've had to do it online, which is unfortunate in some sense because you lose that kind of social interaction, which is what people want. But on the other hand, we're able to get bigger name speakers because they don't actually have to come to Iowa at the end of February, which is amazingly hard to convince people that this is a good idea. And it's traditionally been the last weekend of February, so it can be really quite cold. And this year we have 4 speakers. John Laird's a professor of computer science at the University of Michigan. Chris Hammond's a professor of computer science at Northwestern. Kelsey Hubner is one of our own graduates from 12 years ago. She's a project manager at Microsoft in Redmond, Washington. And Casey DeRue is a local faculty member in the Department of Physics. The talks are all about computing. They're online through Zoom. This year, though, we're going to try to have the social events in person anyway. So you're welcome to take the talks on Zoom or come to the auditorium and watch the talks on the screen. And then after that, there will be a social event on Friday night and one on Saturday night. This is free. Anybody can come. We do ask that you register at this website. You'll be getting an announcement about it in the mail shortly. So please do consider doing this. It's a good way to meet other CS students. Oh, it's finally working. All right, you should have read Think Python Chapter 8 or Chapter 6 in the other book. There's a new reading assignment, which is Chapters 10 and 12 in Think Python, or Chapters 8 and 10 in Python for Everyone. We're catching up with all the data types. So in the books, you get all the operators, not just the ones I show you in class. At some point, I will release to you a cheat sheet for Python, which is a 2-sided, print it out and carry it with you kind of short reference for Python code that has many of the most commonly used operators and data types on it. It's the sheet that I staple to the back of the exams. The exams are closed book, but you are allowed to have this one sheet, which I provide on the exam itself. So you don't have to quite memorize everything, right? All right, I graded question of day 1, 155 submissions, which is a little low, given that there's about 190 students in the class, but give or take. 148 of them earned a point, so a very high success rate, which I sort of expected because it was a very simple problem. It's a lower success rate on Hawk IDs. There were 11 people who used the wrong Hawk ID. Numbers, email addresses, typos. Be really careful with Hawk IDs. I complain about this a lot because it's very labor intensive for me to find a Hawk ID that doesn't match and try to figure out whose it is. Sometimes I have to resort to guessing a misspelling of a name or something, and it would be much easier and important to use your Hawk ID all the time correctly, so please be careful. It's a favor for me. Okay, I talked about the solutions question of the day in class the other day. Today we're going to look at Lab 1. What you got in the email, how many of you got the email? Okay, so you should have gotten an email with a PDF file attached. And let me tell you why. I used to send the Python file with the output of the autograder, but I can't do that anymore because University Email strips Python files as executable attachments. It's kind of a stupid thing to do, but they do that. They don't, however, strip PDF files, which also have executable code in them. Anyway, so what I do is I convert the Python code to PDF and attach that. If you read the document you get, you'll see that it is your submission, and then there's a section added at the end that shows you the test that you failed, and then the score, which in the case of questions of the day is all or nothing. It's either right or it's wrong. If you have questions about how you were graded, the best way to do this is post your question on Piazza with your code embedded and say, why did this give me an error? I don't understand why this is wrong. That's how you learn, so please do post. Okay, Lab 1 should be graded later today or early tomorrow. Question of the day comes out after half hour after class, and it's due on Friday. There will be another one on Friday. Okay, questions? Everybody on board with this? All right, the questions of the day at the beginning are really easy. So if you're skipping them thinking that we're going to drop them anyway, don't skip the easy ones. Do these. At least do these. You can skip the harder ones later if you insist, but these are like gimmies. All right, let's take a look at the 5 problems in Lab 1. The first one was heading. The specification tells the story. In all of these, the trick is read the specification carefully. That's what you have to match. In this specification, there are a few operative words. The important ones, I seem to have lost my highlighting. The important ones here are that it takes a string that and returns an integer corresponding to a compass heading of that runway. And the way to think about this is it takes a string as input, so I have to convert that string into an integer first and foremost. So the only thing you have to do in this function is convert a string to an integer so that you can do some math on it. And the math is to multiply that number by 10. Runway 9 is 90 degrees. Runway 27 is 270 degrees. So that's all there is to it. Just return the value that's the product of 10 times the integer. If you forget to turn it into an integer, it will fail because 10 times the string 9 gives you what? Some of you probably did this in the lab. Gives you 10 nines as a string, right? Because you're multiplying an integer times a string, gives you a string that's that many copies of the original string. So this is all about remembering to convert inputs to the type that they should be. Now, I want to show you a function that some of you turned in instead. And there's a difference between this function, which is the correct solution, and this one, which only looks correct. And the difference here is that print and return are not the same thing. It's a little bit confusing, but let me show you why. So, if I take heading 10 plus 10, we know that this, actually I should have used a string here. I blew the slide, but that's all right. This will still work because an integer of an integer is still an integer. But heading 10 plus 10 should return 10 times 10, which is 100, plus 10, which yields 110, which is exactly what I expected, notwithstanding that I messed up that string argument. What about the alternate interpretation, heading print of 10? These two functions are identical, except here we use a print instead of a return. What will this do? Well, it will take the 10, convert it to an integer, again, already an integer, multiply it by 10, which yields 100, and print that value. So I will see 100 printed because I told it to explicitly print it, and then it'll fail. And the reason it'll fail is it'll give this error that says unsupported operand type S for plus. None type and int. Well, this is weird. I don't know what a none type is, but I can see here that the only operation I had in here, right, is this plus sign, and it looks like I've got something plus an integer, and that something is a none type. Well, we'll see nones later, but the whole idea here is that this return keyword, the return statement that returns this value, is what gives you the ability to use the function call as a stand-in value. In other words, when I see an expression with a function in it, I substitute for the function call the value it returns. But here, this function doesn't actually return anything. What it does, it prints out for you to see something that you computed. But then it returns a special value. And the special value it returns is called none because it doesn't return a value. And when you use the heading print version, when you use this version, what happens is this thing prints out 100, which isn't actually what you wanted. It prints out 100, and then it tries to add 10 to nothing. And it says, I can't do that. So when the specification says, and returns an integer, or returns anything, you better have a return statement. If you're using a print statement instead, you're just fooling yourselves because it almost looks like it works. In fact, if I were just testing heading and I had written it this way, like heading print, it would have worked fine because I would have tested heading print 10 and I would have gotten 100 back. It says score, game over, I'm done. But it's wrong because it doesn't actually return the value. It just prints it. Is this clear to everybody? It may not be really clear yet, and that's okay. For those of you who are just starting, this is confusing. But remember this, it's a little bit like strings and tuples are immutables, lists are mutable. Print and return are not the same thing. We should put together a top 10 list of sayings for CS1. Print and return are not the same thing, should be 1 or 2. All right, let's go on. Inverse heading. Here's another specification, takes a string representing the large block. So this looks a lot like the original headings function. The difference is that we're going to return an integer that corresponds to the compass heading of the runway from the other side. So the way to do this is using modular arithmetic. The easy way to do this is just the same as the first problem. So there's my first problem solution. And I'm going to add 180 degrees, which means go around from the other side, right? So see it from the other side of the compass. And I'm going to do it modulo 360, so I get a number between 0 and 360. That's all there is to it. But I put this statement in, or this function problem in, because I want you to notice that it shares a lot with the original problem. The problem we just solved, it shares all of this part. And if I've done the original problem correctly, then I may as well use my solution from my previous problem and just say, this problem is just like the original problem, except I'm going to add 180 degrees to that compass heading and take the modulus 360. When I do this, when I reuse the function I've already solved, I make the maintenance of this code, and I'm talking, there's not a lot of maintenance to a function like this, but in the limit, if I decided later that I had the heading incorrectly specified in my original problem, I could go back and change it and not have to change this at all. It would follow. If I repeat the code in 2 functions, I have to go back and correct it everywhere. So I'm just trying to point out that if you have built a function to do something, and you're asked to do something that's a minor extension of that, by all means, use the original function as part of your solution. It makes your code easier to understand and for people to read, certainly. In the long term, it will make your code more maintainable, more robust. Feasible triangle. This is the old high school geometry thing, that if you have 3 legs of a triangle, any 2 of them have to exceed the length of the third, or you can't make a triangle out of it. But what's unfortunate about this thing is that many people will just check one combination. I'll say if x plus y is greater than z, we're good. But in fact, you've got to check all possible combinations. X and y against z, y and z against x, and x and z against y. Moreover, in the specification it says you need to be sure, actually, I have to get a new one of these. This is my backup, and it doesn't work either. In the actual assignment, there was more text that's left out here that reminds you that the line segments must be greater than 0. So the solution I'm after is actually something like this. Check that x, y, and z are all greater than 0, and that x plus y, x plus z, and y plus z are greater than the other thing. Each one of these little expressions returns what kind of value? Returns a Boolean. And I use Boolean connectors, or logical connectors. So every little part of this evaluates a true or false, and I'm asking all of them to be true for this function to return true. So whenever you get a function specification that says and returns true or false, you can think about using logical connectors to make the evaluation, the writing of the function easier. But before you sit down and immediately start typing your code, ask yourself, am I covering all of the conditions or not? So this is one problem that a lot of people didn't get right because you didn't cover all the conditions. Okay, next one, explode. These functions are all kind of made up, right? I sit there on Monday night and think, what function can I make up that people aren't going to find if they Google? So I get some weird names. But basically here, two strings. I want you to combine two strings with taking multiple copies of each in some weird way that nobody will ever want you to do it again. So here again, the trick is just read the specification carefully. Look at the example that's always provided. Make sure you understand how the solution of the example was derived from the inputs, and then you do the same thing. So here it's quite simple. I take the first string, multiply it by the length of the second string, concatenate it with the second string, multiply by the length of the first string. That's all there is to it. Okay, chain if S1, S2. Again, arbitrarily stupid function. Takes two strings, and if S1 is not an S2, if S1 is not a subsequence of S2, then I'm going to return S1 and S2 concatenated together. Otherwise, I'm just going to return S2. So there's a lot of ways to go about this. Here's perhaps the most straightforward, which I think many of you elected to do. You simply have the invocation, an if statement that checks to see if S1 is in S2. If S1 is in S2, it returns S2. Otherwise, meaning S1 is not in S2, it returns the concatenation. Now, one thing to notice about this solution, and solutions like this, is that every path through this function evaluation needs to end with a return statement. In other words, you have two choices as you go through this function. If S1 is in S2, then you're gonna go into that first branch of the if statement, and you'll never even look at the rest of this code, but you'll return something. However, if you don't have an else condition that captures anything that doesn't go in the first branch, you will fail to return a value in some circumstances. In this case, precisely when S1 is not in S2. So if you ever have a function where you have an if like this, you need to make sure that both paths through that function end with a return statement that returns the appropriate thing. So this is pretty straightforward. I want to point out that logically, it is exactly the same as this alternative interpretation. In other words, notice that here I have an if and an else. If the condition is not true, I take the else. But here, if the condition is true, I return. The return exits the function. Whenever you get to a return statement, that function's done. You go no further. So I don't even need the else statement here. I can just say, if I don't get to that first return, then that's what I want to return instead. And those two functions are completely logically equivalent. Finally, I could go even one step further and write my function like this, using Boolean expressions and connectors, and using values that are not Boolean. So S1 and S2 is a Boolean, right? Returns a logical expression, true or false. But S2 is not a Boolean. S2 is a string. But remember that even values that are not Boolean have Boolean interpretations. We know that 0 and 0.0 are both equivalent to Boolean false. Any other number is considered true. So one little known, well, often known, but beginners sometimes find this off-putting, I can evaluate this one line, and it is logically equivalent to that statement in the other function. We'll see a little bit more of this later. But for now, just realize that even non-Boolean values can be used in logical expressions with the logical connectors, and they have a logical interpretation, but they don't always return just true or false. Okay, questions? All righty. So when last we met, we had finished, I believe, lists and tuples and strings. Today we're going to talk about ranges. So a range is an immutable sequence type, like tuples and strings, that contains integers. It's only a sequence of integers. But what's interesting about ranges is they are not explicitly represented. And I'll show you what I mean by that. Okay, so this is working again, thank goodness. So if I ask to construct a range with the value 5, what I get back is this construct. It is actually a sequence type, even though it doesn't look like any other sequence type. It doesn't look like a list, doesn't look like a tuple, doesn't look like a string. Instead, it's an implicit type, meaning you're seeing a printed representation of this thing, but inside it has a different meaning. When you see a printed representation of a list, the list is the list, and you can see exactly what it contains. Here, you're getting this special printed representation, and that tells me, because I know what it means, that internally, Python has a different representation. I just don't know what it is. So let's take a look at what this range means. Range is really a sequence here with one argument, 5, is a sequence here of 5 integers, starting from 0 and increasing sequentially by 1. So this range expression here really has implicitly those values in it. So I can index the range and ask for the third value, which returns a 3, 0th value, first value, second value, third value. I can create a new range called 1, 11, 2. And here, what this range tells me is it is a range of 5 numbers that start with the value 1, up to but not including the value 11, with a step size of 2. So in other words, 1 plus 2 is 3, plus 2 is 5, plus 2 is 7, plus 2 is 9, plus 2 is 11. That's too far because it doesn't include 11. So it's 5 values represented implicitly behind that range statement. But I can index it just like it was a sequence. I can say, take these 5 values, that's what they look like, starting from -2, -1, -2, up to, but not including the 5th one, 1, 2, 3, 4, 5. So actually it's just a range of 1 element, and -1 is that 1 element. I get back 9. Something's wrong here. Oh, no, that's right. 2, 1, 2, 3, 4, 5. Yeah, it should be a 6. Apologize. There's something wrong here. -2, 0, 1, 2. 0, 1, 2. Oh, no, sorry. 0, 1, 2, 3, 4. There's only 5 elements, so that's fine. So -2 to 5 is -1, -2. So starting from 7 through 9. And the -1 of that is 9. So this is correct. Now, what's disconcerting about this is if I had shown you here, instead of this range, a tuple that looked like that, you would have no trouble interpreting that. But because this is implicitly represented, it's a little weird. Right? It's hard to understand. You have to remember, well, what does that mean? And then you can sort of parse it. So why do we have ranges? Well, imagine that I expressed a range from 1 to 10 million. And I just type range 1 to 10 million by 1. Python would have to respond by typing out 10 million integers. And then you would have to count those 10 million integers to figure out what subsequence you wanted. Range is implicit, which makes it really powerful for dealing with very large sequences of integers. And that's what it's good for. We'll only see little examples, but all of these examples are just as concise if there's 100 million elements in that sequence. So it's a convenient way to deal with very large structures and manipulate them handily. Now, a range like this implicitly gives me a sequence of some sort. I can convert that sequence type to a tuple, and I can convert that tuple to a list. And what I'll get back here is the range 0, 0, which is a range of 0 elements, starting at element 0 and ending one less than element 0, so the empty range. Converted to a tuple gives me the empty tuple. Converted to a list prints out the empty list. That's the value it returns. So I can freely go back and forth around these different types. There are some constraints. I can't take a list that is not made of integers and try to turn it into a range because ranges are integer only. Moreover, some lists of integers are not regular lists. A sequence like 1, 3, 4, 17, 22 cannot be expressed as a range. So while I can go from ranges to other sequence types, I can't always go the other way. So the general form of a range is it takes 3 arguments: the starting point, starting integer, the stopping integer, we stop just short of the stopping integer, and the step size. If you see a range with just 2 arguments, then it assumes the step size is 1. So from 0 to 5 by 1 is 0, 1, 2, 3, 4. And if you see just range stop, like here, it assumes the step size is 1 and the starting element is 0. So that's the semantics of range. It may look a little weird to you. It's incredibly useful in practice. Let's take a look at some examples. Range 330 by 3 gives me the answer evaluates to just what looks like I typed in. In other words, this printed representation of that internally specified sequence. It actually looks, those are the numbers represented by this expression. It has a length like every other sequence type. There's 9 elements. I can index it just like every other sequence type and get back the last element. I can take subsequences of it like we did before and index a single element of that subsequence. I can index the last element of a subsequence or a range where the step size is negative. Notice that this range, unlike the other ones, you start at 10, you go backwards by 1, minus 1, until you get to 2. So up to and not including 2. So that means this range is 10, 9, 8, 7, 6, 5, 4, and 3. Minus 1 will give me the the last element, which is, let's see, 10, this is minus 1, will give me the last element, which is 3. 10, 9, 8, 7, 6, 5, 4, 3, 1 short of 2. So step size can be negative. Same thing, taking the first to third elements here. Notice that when I take a subsequence of a range that can be expressed itself as a range, I get back a range type. So when I'm manipulating ranges and indexing and slicing them, if the result can be represented as a range, I get a range. If it can't be, if it's a single element, say, then I just get the single element. What about this? Well, this is the same expression that was returned as a range converted to a list. That would be 9, 8. And there's my list, 9, 8. So it's going to take a little bit of thinking about ranges so you get facile with this. But I want to point out that slicing, which we've talked about before with the little square brackets and taking from to with the colon, has amazing similarity to range. The expressions are really similar. So for example, assume I have a string, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I use the full form of that slicing expression. We've seen indexing with a single square bracket and a number. We've seen slicing with a square bracket and 2 colon-separated numbers. But the full form has 2 colons and 3 numbers. And the form here corresponds to the range numbers, starting with this, ending just short of this, and indexing by 2. So I would get from this string, with an indexing expression 182, I would start at 1, which is here, and go by 2. So 1, 3, 5, 7, up to, but not including the 8th element. And I get back a string, because this is a string, I get back a string that uses that same kind of range indexing to create a new string. So do you all see the analogy between range and this indexing scheme? So range seems like this weird thing, and why do I have to learn it, and I'm not going to use it. But in fact, you're going to use this kind of slicing and indexing all the time. And if you know how to do that, then you also know how to use range. They're really the same thing. Let's look at another example. S3 colon assumes that the ending remark here is the length of the string or the right end of the string. So the length of this string here is 10. So this is the same as S3 colon 10 colon 1, because the default step size is 1, and an unspecified end is going to be the length of the sequence. So this gives me 3, 4, 5, 6, 7, 8, 9, just like you'd expect, from the third element all the way up to 9. Notice that I'm doing something a little sneaky here. I'm using a string that starts with a 0. So when we index the third element, it's going to be the number 3. It's not always the case, obviously, right? It's just to make this example easier. What about here? Well, just like range, we start with the 0th element, up to but not including the third element, and by default, including every element, so a step size of 1. Well, what happens here? I'm asking you to take the string, and I'm indexing the slice that starts by default with the first element and ends by default with the last element. What I get back is a copy of the original sequence. In this case, string S. I have a new string that looks just like the old one. And this also works if I put 2 colons, because everything then defaults. You start with the 0th element, you end with the last element, and your step size is 1. Everybody okay with this so far? Clear? Now it gets a little fun. What about this? The default starting point is the beginning. The default end point is through the rest of the list, the length of the list, or string, or sequence, or whatever. And by -1 does what? It goes backwards. So this is a handy way to create a reverse copy of any sequence. It takes the sequence, it makes a copy of it, just like we made a copy of it right here. This makes a copy, returns a copy of the sequence. But this copy goes from the end to the beginning. So this is Python shorthand. This is Python shorthand for the reverse of a sequence. And by the way, you can do this to any sequence, including to a range. You can say range 1, 10, 1, and then use this. And what you'll get back is a new range that says range 10, 0, 9, 0, 9, 0, -1. It'll give you the range that goes backwards. So it's a way of inverting any sequence type. What about here? Well, this is the same, except we're going to start with element 1. So the thing we get back here is we're going to go starting at element 1, going down, reversed. Element 1 is here, 1, 0. Reversed gives me string 10. Okay? So a lot of fancy stuff. How about this one? -3, starting from the beginning, or the end in this case, because I'm going backwards, by -3, starting with element 0. I'm going to go backwards, and I'm going to get 9, 8, down to -3, just one short of it. -3 is 7. So that is 9, 8, reverse, because I'm going right to left. All right, so don't be freaked out when you see these. Practice with these a little bit so they become second nature. I think, in my book, these kinds of things are more confusing than they're worth. If you write code like that, it's just awkward, unless you comment it and explain what it is you're doing and why you're doing it. But this idiom here of reversing a list, or a sequence, that's very commonly used. The stuff where you reverse subsequence is much less so. But you should at least be pretty conversant with all of these types here, all of these indexing examples. Okay, so that's range. We're done with sequence types. There are others. We won't talk about them in class. You can read about them in the text. But we're going to start the next mapping types. This is probably the most useful data structure in Python. It's a data structure that exists in other languages. Some of you have written code in other languages and may have encountered what are called associative arrays. That's what mapping types are. Mapping types are really a generalization of lists. So think about what a list is. A list is a mutable sequence of elements that are indexed by an integer. Because they're a sequence, there's an ordering, I can make sense of saying, give me the first element, the second element, the 15th element. So that's an indexing into a list. And the list contains things of arbitrary type. It can contain strings mixed with numbers, mixed with floats, mixed with tuples, anything you want in a list, unlike an array. Dictionaries are a generalization of list types. In list types, you can only index or select an element of a list by using an integer to describe it, the index. In a mapping type, instead of only integers for indices, you can have arbitrary things as indices. So you can use strings to index a mapping type. This is really useful. Imagine for a second that you're building a database of all the students in the class, and maybe you want to have in it the grades of the student, and you want to index this thing, this structure, by Hawk ID. Rather than have to index and say, Hawk ID ABCD is actually student number 72, or knowing the student ID number, knowing the Hawk ID, you can access the student record. And that's what a mapping type does. So a lot like lists, they're mutable and indexable, but they don't require integer keys. And because they don't require integer keys, they are not sequence types. They're not ordered. So the other thing that makes a sequence type is that there's this relation. This element comes before that element. Mapping types, there's no relation. Elements are just in the type, and you retrieve them by virtue of their key, but there's no implicit order in those types. So let's take a look at what it looks like. So dictionaries look a lot like lists, but they get curly brackets instead of square brackets. For that matter, they look a lot like tuples with curly brackets rather than rounded brackets, but dictionaries are mutable. In a dictionary, we have comma-separated elements, and each element consists of a key, colon, a value. So in this dictionary here, here's another example of a dictionary where the values here, the keys here are all single characters. So the value of this indexed with the character B is going to be 3. Here's another one. This one uses keys that are integers. So it sort of looks like a list because it's got keys that are integers, except that these are not ordered. There's no implicit order in the mapping type. So if I type in this dictionary, you're going to notice that I typed in 4 values, but I only got 3 back. It's another quirk of dictionaries. Any ideas why? Go ahead. Okay, so the answer is that here I have a 2 key associated with the value false, but later on I have a 2 key associated with the value true. And in a mapping type, there's this one-to-one relationship. A key, whatever it is, can be an integer, can be a string, can be a range, I don't care what the key is, maps onto one and only one value. And here I have 2 conflicting values. Which is it? 2 is a false or 2 is a true? And the answer is, when you try to make a mapping type that has keys that are ambiguous, it's only going to show one of them. The other one gets overwritten. So here it's chosen to keep the last one that's typed in. So I type this in, but I get back a dictionary that has unique key value pairs. All right? And by the way, the ordering here, 1, 2, 3, completely accidental. If you type it in, you might get 3, 1, 2. Doesn't matter. It's a collection, not a sequence. So let's try some. So here's a mapping type. It's the same one I showed you before. All the keys are unique. They're not in order. I can index it by asking for a letter, A. And I look in here and I find the A key. So the value here is 4. So it does a retrieval from that mapping type and returns the value associated with that key. Here's another one, same thing. Actually, is that a different value? Yeah, it's a different dictionary. With the value C, or sorry, the key C, there's the key, there's the value, I get back to 2. Again, with an E here, but guess what? I don't see an E key in that dictionary. So I get back an error. It says, hey, I don't know E. Key E does not exist in this type, in this dictionary. Can't do anything about it. Okay, now we can get really arbitrarily messy because we have all these different types and we know how to interpret them. So what does this expression do? Good Lord. Well, let's do it a little bit at a time. So on the outside, we see that bool in parentheses. So whatever this thing in here is, we're going to return the logical interpretation of that thing as a Boolean. So we know this thing's going to be either true or false. Because whenever you cast something a bool, you get a true or a false. So let's look at what the thing inside this, friends, is. There's a dictionary here that maps true to 0 and false to 1, which you'll notice is, by the way, the opposite of what usually interpretation is. And that dictionary is indexed, it's indexed by, looks like a logical expression. So P in Prodigy, the value there is what? True, because this is a logical expression. It returns a true. And true, by the way, is a key in this dictionary. And the value of that key is 0, which I then convert to Boolean, and what do I get? So the whole thing here is to get a false. The point here is these are ugly expressions you would never write. But knowing the rules of evaluation, you can figure out what they evaluate to. It's good practice. Do a lot of these so you can really feel comfortable and confident with what Python is doing. All right? We have 8 minutes. We may be done with data types today. We're going to talk about the last data type, sets. Sets are mutable, unordered collections. Dictionaries, by the way, were mutable, unordered collections indexed by arbitrary expressions. Sets are mutable, unordered collections that aren't indexed at all. So in a sense, that's a special case of a dictionary where you only have keys and no values. So here's a set. Curly brackets, looks a lot like a dictionary because they're special cases of dictionaries. You can read this as a collection of these values. But what do you remember from high school math and from the fact that dictionaries don't allow duplicate indices? What do you think this comes out to? How many elements in the set? Just 3. And Python will tell you, I know 1, 2, 3, nothing else in here because they're all just copies. So sets are uniquifying collections. You give it a list of stuff, and it gives you back a set of the elements of that list with duplicate entries removed. Incredibly useful. So, I can take a range of 5, which is what? What numbers are in the range of 5? First of all, how many numbers are in the range of 5? Hold up your hand with your fingers. Okay, I see a lot of 6s, but you only need one hand. Range of 5 has 5. Why? 0, 1, 2, 3, 4. This is the end. You go right up to, but not including that stop value. So starting at 0 by default, 0, 1, 2, 3, 4. 5 numbers. So the range of 5 are 5 numbers. Turn it into a list. I get a list of 5 elements. 0, 1, 2, 3, 4. And now, when I turn that into a set, I get a set of elements because they're all unique. 0, 1, 2, 3, 4. Now, as I type these in, I realized I did a stupid thing. I put them all in order because I think that way. But in fact, in Python, these are not ordered. So the set 0, 1, 2, 3, 4 is exactly equivalent to the set 4, 3, 0, 1, 2. They're the same. It's collections of 5 elements. If the elements are the same, the sets are the same. What about this? Range 2 through 6 is 2, 3, 4, 5, 4 elements. Turn it into a tuple is a tuple, 2, 3, 4, 5. This is a sequence type, tuple is a sequence type, so they're still in order, 2, 3, 4, 5. But once I turn them into a set, I get the collection 2, 3, 4, 5, which is not ordered. What about here? The set of a dictionary, there's a hint up here, special cases of dictionaries, the set of the dictionary is simply the set of the keys in the dictionary. The keys are 1, false, true, and 5. But here, what happened? I lost one. 1, false, true, and 5. Why did I lose one? Anybody? Well, which did I lose? The 1's there, the false is there, the true is not. But 1 and true are internally the same thing. So the set only kept one of them. In fact, even this dictionary, once I type it in, would have lost one of them because they're the same. All right, so sets lose. So let's back up for a minute. We started talking about sequence types. We had immutable sequence types like strings and tuples. We had mutable sequence types like lists. We had partially mutable sequence types like, mutable sequence types like tuples, strings, and ranges. We had mutable sequence types like lists. We had mutable collections, index collections like dictionaries. And now we have mutable collections. And when I say collections, I mean unordered, like sets. And sets, you can't index because they got no key. What would you be indexing? Say, give me the element that corresponds to 1 in a set is the element 1. So indexing doesn't make sense. But they have all sorts of really special operations that do. And yeah, we're about to get to none. Let's not do that. I'm going to skip for now the set operations. You can index sets, but the operations union, intersection, proper subset, and so on are really useful. And so you'll be using sets a lot in this class. So I don't introduce them right away because I'm going to show you an example later. But this is the end of our built-in data types. When we look at our list, we've seen the numeric ones, we've seen logical, we've seen the sequence types, both immutable and mutable. We've seen the mapping types dictionary, which are mutable collections with indices, and the mapping type and the set type, which are mutable collections with no indices. So that's the end of the data types that are built in. Now we're actually going to start doing something with them. I will see you on Wednesday. And it looks like Panopto managed to hold it together today, so that's a good thing.